Hello again. This is to show you what is inside the notebook that illustrates how to implement your own version of KNN. First of all, what we do here is to read the data. I'm not using the dataset package here. I'm simply using pandas. PD is the short form of pandas. I normally import pandas as PD. This is an alias for that name. And what I do is to simply read the CSV file, which is the dataset that I already uploaded to the campus online. From a previous overview of the dataset, I know that I have to convert into float these columns that I put into this list. So I simply specify that these columns to be converted need to be set to this type float, right? This is a very simple data transformation here. As you would see, I'm not running any statistical process, no exploratory data analysis, because what we want to use is KNN, and there is no strong assumptions about the distribution or correlation between the features in this type of methods. So no really needed in this case. The target variable is a string, which is uh, like this, B or something else, but I want to use numbers because KNN works better with numbers, let's say that. So I apply this lambda function, which is, okay, for every row in this column of this data set, simply apply this function, which is if you find a value which is equal to B, then assign to value uh, this numerical value, 0.0, else 1.0, right? So very easy. Transforming these strings or characters into numbers and converting into floats. There is another column called ID that I will use at index, and the result is like this. The only remaining thing is to simply rescale. I will overview very quickly how to do that. I specify the target in this column, and the features the rest of the columns, everything but the target. And I will use the robust scaler to transform everything to values in a normalized interval of numerical uh, values, so to say. The final result can be seen here in this sort data frame. You can see numbers between probably -3 to +3, something like that. It's a very well-scaled data frame. Now we can start working with that. So the code contains 4 functions that I will use to illustrate how KNN works. Remember that the whole point is to measure whenever I want to classify a new entry is to compute what are the closer individuals or samples from the data set to the new sample that I want to classify. And to do that, I need this Euclidean distance function. One of the exercises to work with another distance function that instead of working with these two vectors P and Q to produce the Euclidean distance will produce, for example, the Manhattan or Minkowski distance. There are plenty of code available in the internet to do that. So Euclidean distance for all the dimensions in those two vectors, P or Q, in this case P, for all the dimensions in that vector, what I say is the distance is equal to the sum of the difference between them, between that component squared, uh, squared, right? There's that. And the final result is finally the square root of that distance, of that sum of values that you can see here, and rounded because I don't want to use many decimal places here. So this is Euclidean distance. You can find many implementations of this. No big deal here, but I need it in a separate function. Next function that I want to use is the distance matrix that I will use from data. Data, remember that, is using not only 2 dimensions, but any number of dimensions and any number of samples. So the number of samples is in this first component of the call to shape. And from that point, what I will do is to compute for every couple of individuals in the data. So I will compare the distance between any 2 samples in the data set. What is the Euclidean distance between them both? For that, I am using this version of, or this implementation, which is not very optimal, that uses two loops. The first one ranges the number of samples, and the second one is also ranging the number of samples. So I am traversing or looping through the whole list of samples in my dataset two times, right? And I put any instances in in I and J. And for each couple I and J, what I compute is, okay, this D row, which is the distance for the value J, is simply the distance between the value at I and the value at J. I'm calling my function here. And finally, this row is inserted or added to the simply to the final matrix this way, right? So in the end, what we have is a matrix D, which contains the distances as is specified here between every single pair of individuals in the data set. And we get into the final function that we need, which is the get neighbors. Okay, as I explained in the slides, to get the neighbors between a point and the data, I need to find in the data which individuals are closer to this point. And to do that, I do this simple trick, which is, okay, go through every sample in the data set. And for each of those samples, what I do is, okay, this point in the data set contains these values, okay? This is the vector of values at this position in the data set. And the distance is simply the Euclidean distance between this point and the point I want to compute the neighbors for, right? So this distance is added to a simple list, which is the distances, right? What I do is to add the sample index, which is okay, at this position or this sample with this index is at this distance of the point I want to compute. So I do this for all the samples, and at the end what I get is a list of distances between every sample and the point I want to classify. If I sort that distance, what I will get is a list of individuals from the lower distance to the higher distance to the point I want to classify. So by sorting this, what I get is the neighbors in the top of the list and the individuals that are much farther from the point at the bottom of the list. So I will only pick up the num of neighbors that have been specified as an argument to the function here to return this list of neighbors that I build by adding only the 3 or 5 or 7 first elements of this list. I return the neighbors and that's it. So this is an example. So for any sample, in this case, I invented completely this sample with 1, 2, 3, 4, 5, 6, 7, 8 dimensions, which is the same number of dimensions that we have in data. If I want to get the neighbors of sample in this data set, using only 3 neighbors, what I get is the index values. So the position in the list of samples in this data that contains the individuals that are closer to this guy. So the individual at position 82, the individual at position 1 and 2 are the ones that are closer to this random point that I invented. So this is it. If I want to use everything that I built so far, what I simply have to make is, okay, from this list of neighbors, I need to get what is the label which is most frequently present in this list to obtain what is the result of the classification, this is called majority voting, right? So predict classification is simply using all the arguments that we need. Okay, the data, the features in my data set, and the sample that I want to classify, and the num of neighbors that I want to use. So the neighbors is obtained by calling the function that we built here, right? So by using only the features, try to get the neighbors for this sample using only this number of neighbors. And the output values are the labels itself. So for all the elements in neighbors, right? So I am going through all the neighbors obtained here. Simply get the target value, the value of the column target, which is the label itself. It will be 0 or 1. And these output values, now I need to know which one is um, most frequent or to compute the majority voting. And to do that, what I do is to convert the output values into a set and using the function max, which is only tell me by counting the number of times each in different key is present in this list, count them and tell me which one is the maximum, right? And that will be the prediction. This is the majority voting. This is how it's done. And that's it. Predict classification will give me the prediction, the label itself, and wrapping up everything and building a single function for all that is simply about calling this function for every row in your test dataset, right? So by using this function, not with your sample, but with a test set, you will obtain the KNN or the classification for those individuals based on the training set that you are using. And that's it. Uh, I hope that you understand how this code works, because one of the simplest things that you need to do from this point is to split your data set between training and test and measure what is the performance of the algorithm on your test set using cross-validation, which is something that I um, explicitly didn't cover, right? So let's work on that. Thank you.